Okay, talking a little bit about Laplace transforms. Not going into a whole lot of detail because everything here is very straightforward, okay? And you've already done an integral of this nature, I think, for the cosine function. And you have to do two integrations by parts, and, you know, like you say, you get a kind of a loop. And that's straightforward for second semester calculus, okay? And a method that you just simply have to know. I'm not going to teach you that method, you just got to know it. And I think you do. Okay. So here's a definition of a Laplace transform of a function. Laplace transform of f of x is this. Okay? Now you said, well, there's an x here and there's a t here. Doesn't matter what's here. Whatever's here can be replaced by anything we want, right? Well, I choose to use t for my integration constant. I didn't choose it, that's convention. Okay? So I'm just following convention when I do that. It doesn't matter what the variable here is, it's a dummy variable. When you do the integration, it's not going to be there anymore. So it doesn't matter if it was an x and a dx, although if it's a dx, you're going to have an x here, right? Okay? So that's straightforward. And you did the Laplace transform of the cosine function, I think. So we do the Laplace transform of the cosine of aardvark. Just to emphasize that it doesn't matter what this variable is called. When I do it over here, it's going to look like this. Okay? So whatever your variable is, it's going to be t when you do the integral. It's going to match the t here. Okay? And then we say that this equals capital F of s. Just another notation, and that's a notation you see in most tables. Okay? This stands for the Laplace transform. So we say the Laplace transform of the cosine of omega t, which you could easily do just by putting an omega in front of this t and doing the integral, right? It's going to turn out to be this. Okay? And, you know, probably assign you to do that. Because now what we're doing is we're looking at the tables because we don't want to get hung up on doing these integrals. But the integrals you do to do at least 80% of what's on that table are equally straightforward. Okay? Sometimes you got to do some partial fractions and sometimes you got to do some other stuff, but it's just standard first year calculus integration technique and not particularly difficult. Okay? Now there are other Laplace transforms that require all kinds of analytical tricks. We're not going to worry about those. Okay? Not going to worry about how to derive them. We're going to use the tables. But you're going to be asked to derive most of what's on the table in your textbook. So, here's the Laplace transform for the cosine of omega t. So what's the Laplace transform for the cosine of t? Well, that would be the Laplace transform for the cosine of omega t with omega equal to 1, which is just this. Clear? Okay? And again, you can verify all this. You've already done, I think, this one. Maybe I ask you to do the sine.
I think it was cosine.
Yeah, but just to show you, you can do it. We're going to see how it's used. First thing we need to do, we're going to be able to take a differential equation and transform it into an algebraic equation, where we just use regular old high school algebra to solve it. Okay? And once we get the solution, we look at the table and see how we can take that solution and find out what it's the Laplace transform of. And that'll be our solution. In other words, we apply the Laplace transform to get an algebraic equation, we solve it, and then we inverse transform that solution back to function space. So it's like, kind of like in linear algebra, you transform a vector space into another, okay? And you can transform back maybe, or transform part of it back, or maybe you can't, depending on the definition of the transformation. You transform I'm misusing terms here, but give you the flavor. You transform a function space to an algebra space, and then you can transform back. Okay?
Do you get the same function?
No, you get, well, if you, yeah, you would get the same function. Okay? But if you're transforming a differential equation, you take the whole differential equation from function space to algebra space, get the solution, and then take that solution and transform it back to function space and get the function that solves your equation. Okay? And that's an overview. You know, it's a very simple conceptually, especially if you've had some linear algebra and are at least aware that there are transformations in the world. And if you know pre-calculus and know how you transform functions by translations and stretches and stuff like that, it's just another type of transformation. Okay? Now, in order to transform a differential equation which involves derivatives, this is going to be very useful. Okay? We take the integral that defines the Laplace transform of f, and we perform an integration by parts. And very straightforward. I'm not going to even point to the thing. You can do this. Okay? And then write it out carefully. We get this. You know, here's our u, here's our dv. And our derivative of that is this. Derivative of this is, well, the derivative of f of t, or du, the differential of u, is going to be f prime of t dt. Okay, so just using that, we assemble this, you know, uv minus the integral v du. We get this. And should have said this integral is from 0 to infinity. It's implicit, but we really should make it explicit, okay? Now, this part of the integral, evaluate this at 0, what do you get? You get f of 0 over s, negative f of 0 over s. Because e to the negative ts is e to the 0, that's just 1. T is 0, so you get negative f of 0 over s. Now, what's this? Well, if you take, you know, the 1 over s, of course, I've factored out here, okay, because it's constant with respect to t. And then this is nothing but the Laplace transform of f prime of t, right? I mean, if I put a prime on this f, then I got to put a prime on this one, right? And now I've got the Laplace transform of f prime of t. So I just say, well, that's, I don't know what that is, but it's the Laplace transform of f prime of t. That's something it certainly is. We don't know the details. We don't know what the function is. It doesn't matter what the function is, as long as it's defined in such a way that this integral makes sense. Okay? And we worry about the details of what makes sense and what doesn't. But not right now. Okay? So we get 1 over s times the Laplace transform of f prime of t. Well, we just set this expression equal to what we started with, because I've got a bunch of equal signs between here and there, and solve for the Laplace transform of f prime of t. I don't have to tell you how to do that. This is what we get. Okay? Now let's just take the equation okay, I hadn't thought of a good equation. We could do higher order equations very easily. By just extending this. What's the Laplace transform of f double prime of t? Well, just replace f with f prime and you get stuff, okay? And it's easy to write out. We're not going to do that right now, okay? So it's real easy to transform higher derivatives of your function, okay? Okay, so anyhow, let's say we have the equation, just y prime plus 5y equals 0, right? Okay. Well, the Laplace transform is linear. That is, if I have a sum of several functions here, I'm going to end up with a sum of several functions here. But then that's just going to break into a sum of integrals, right? Well, for that reason, this thing is linear. That means the Laplace transform of y prime plus 5y should equal the Laplace transform of 0. Okay? I mean, just look at the way, if I integrate both sides of this with an e to the negative ts from 0 to infinity, and then integrate this with an e to the negative ts from 0 to infinity, it's got to be equal, right? So if you just think about how this thing's defined, it's got to be equal. I'm waving my hands over some things, but that's pretty much a true statement. So we can say that the Laplace transform of y prime plus 5 times the Laplace transform of y equals 0. Now obviously the Laplace transform of a function that's identically equal to 0, well, this is going to be equal to 0, so we're going to be integrating 0, right? You're going to get 0. Okay? Now, how did I get the 5 outside of the Laplace transform? Well, it's linear, and that's part of linearity, and that comes from the linearity of the integral. If I have a 5 in front of f of t, I can bring that 5 out here, right? Okay? So that's why I can do this. Okay? Now, what's the Laplace transform of y prime? Well, down here that's y of 0, right? Plus s times the Laplace transform of y. Right? Plus 5 times the Laplace transform of y, and that's equal to 0. So, what do we get? We get s plus 5 times the Laplace transform of y equals negative y of 0. So the Laplace transform of y is negative y of 0 over s plus 5. Okay? Now look in your table. Now negative y of 0 is just some number, right?
Yeah.
So we could think of that as negative y of 0 times 1 over s plus 5, right? So what would 1 over s plus 5 be the Laplace transform of? Go ahead and look it up. I'll be back in a minute.